Numerical integration. Nice thing about numerical integration. Anybody know anything about numerical integration? Anything like that? I just realized I forgot to put in the goals. What a shock. It is indeed similar to numeric differentiation, but it is even more elegant. I would say differentiation suffers in a lot of ways, but the integration formulae are pretty cool, actually. That's one of them. Yeah. That's definitely one of them. This lecture is okay. Wednesday's lecture is super cool because then we get to Gaussian quadrature, and that's like the fundamental finite element method and stuff like that. And that's where things really start to get cool. Cool. I did actually have glasses from grade 12 until, from grade 5 until third year? No, grad school. Like second year master's, and then I got laser eyes, so I am entitled to do this. All right. So why do we want to do numerical integration? Let me turn up the brightness because apparently laser eye didn't work that well. It is particularly useful because analytical integrals may be hard to find or they just might not exist at all. Complete possibility. Integration also tends to damp the experimental noise, whereas differentiation tried to basically amplify it, right? And the whole reason it does that is because you're just summing stuff up, right? So if you sum the answer and then the answer minus a bit, you've actually canceled out those errors. So that's pretty cool. In 1D, its integration is simply finding the area under a curve. Hooray. All right. We're going to talk about definite integrals today. So in this case, it's where we have the integration limits A through to B, in which case this is called numerical quadrature. I don't know why it's quadrature, I guess, because you're basically, well, no, a lot of the methods are kind of finding the area of a four-sided object. So maybe that's why, but I don't actually know. Exercise for the student. Has anybody ever noticed that the integral sign looks like an elongated S? And do they know why? No? Anybody know why? Literally sum. Apparently it's Latin for summa, which is literally the summation. Which is good because that's exactly what we're going to be doing. I think that's sigma. Yeah, but that one's Greek. This Latin. I'm trying to explain to my 6-year-old like why some names are like Greek and why some Latin. And yeah, it's just a gong show. No. I can actually. I heard a great explanation. It's because English isn't actually a language. It's 3 small languages dressed up in a big, what do you call them? A trench coat, thank you, pretending to be a real language. That's what. What's that? Well, there's the Latin, there's the Romantics, there's the Germanics. I don't know what the third one would be, actually.
All the Romantics together. You can say the Romantics Latin, but actually we get stuff in Latin, but also from French, Spanish, and Italian.
Confusing for me. 3 kids in a trench coat. All right. So we're going to talk about 2 different cases. First one being where you have f of x, and the second one being where you don't have f of x, but you have it tabulated. So discrete, you have a discrete function, a tabulated function. The methods that we're going to talk about are valid when you do have f of x, but nobody does them because Gaussian quadrature kicks their ass. Newton-cotes integration formulae is a family of methods that all basically operate on the same idea. That being, we subdivide the integration domain into small parts. This is literally how we derived integrals, right? Like you subdivide it into small parts. On each subdivision, you approximate the real function with some polynomial. Polynomials can be integrated exactly, and then you just sum up everything together. I have a nice little widget here that stops all this fun stuff from constantly looping because that just drives me insane. But every once in a while, I need to reload it so that it'll actually show the animation. So this is an example of a function being subdivided. This particular one is actually a midpoint method. We'll talk about what that is. But you get the idea that as you do more and more subdivisions, you get closer and closer to the real integral, literally integration, right? Yeah.
Why is this better than using like a curve fit model and you have a function this integrating? Is it because of computational complexity?
No. It is one of the that was one of the questions on the exam though. Anybody? Why not just curve fit the entire function and integrate that? Sounds painful. That's a big one. Keep going. What happens when you integrate or what happens when you curve fit in order 10?
Oh, the frequency.
Yeah, everything, it just blows up in your face. So the logic with this is the exact same for the splines. You want to avoid the high order ones to avoid that run just phenomenon. So SymPy is symbolic.
Yeah. Like, or like, wouldn't you not even, your integration, right?
Yeah.
You could just do it directly. You wouldn't even have.
Well, what would you be doing directly?
I don't know.
Wait, watch, and ask me afterwards. Okay. Since we're doing summation over the subdivisions, there's no obvious need for consideration of continuity, right? So what that means is that every single block here is independent. When we looked at things like trying to do a curve fit with the splines, for example, we had to say that it was continuous from one block to another part, and the first derivative was continuous, and this, we don't need any of that. This is literally just flat out summation, one block plus the next block plus the next block. It means that we can apply divide and conquer algorithms. So redundant programming is very effective for integration. It also parallelizes very easily because you can just farm them out and then bring them together. There's no communication between these guys. No. Okay. So obviously, as h goes to 0, the number of boxes goes to infinity, right? And the approximation becomes analytic, literally the definition. Okay. Different algorithms will converge to the true integral at different rates. Surprise, surprise. Depending on the step size h. We're back to that concept. And of course, when we have that fact, we characterize our methods in terms of the order of step size this time. And this is where your answer is going to come from. It does depend. So we can use certain properties of the Taylor expansion to eliminate higher order errors. And that's how we get these higher order integration methods. Let's see. The error has to be considered on two levels. Now, so this is a little bit different. The two sources of error are integration of the approximate polynomial within a subdomain in the first place. If that were perfect, then you just sum all of those and you get the exact answer, right? Or it's the fact that you're even breaking up the entire domain into a finite number of subdivisions. Because if you did an infinite number of subdivisions, right, then the approximate function is just the point, and again, you have the exact answer. So the deviation, your error, comes from those two different properties, and you have to kind of keep them in mind. But what this means is that you want to, again, you want them to be equally spaced. Because when things are equally spaced, then you can exploit certain symmetries and properties to eliminate the higher order terms. And we're going to throw back to the Taylor series for to show that. Yeah, there's nothing really stopping you from doing uneven domains except for the increase in order, right? So there are some methods. Actually, there aren't really methods to do this. Well, there is kind of. No, there are methods to do this. Actually, this is finite element method. Yeah. So put a pin in this idea. Let's say don't do that. And then on Wednesday, we'll say do that. Yeah. Yeah, I already mentioned, so the formulae here are valid for both if you have the function and if you only have tabulated data. Don't do it if you have the function. There are better techniques. And let's get into them. The first one is Riemann integrals. So these are Newton-cotes order 0, right? 0 order polynomial is a point, right? Constant value. Okay, so the question is that if you have a subdomain now, which point? Right? Anybody want to take a guess? Gotta get my marker. Do you have an idea? What's that? Oh, somebody, well, I thought there was a hand here. Yeah. Midpoint is definitely 1 and is actually the correct answer. But before you get to that one, you're supposed to see the left and the right ones first. I'll come back to that one. I'll come back to that. Okay, so beginning at the simple answers is the left and right Riemann integrals. Basically what we're doing is we're taking the function value at either the left side or the right side of your function, saying that it's a constant along there, and then literally the area there is just the constant times the height. Right? Pretty straightforward. There are the formulas here. The difference here is your counting. Right here, you start from 0 and go to n-1 because you're doing the left side of your interval. On here, you're taking the I starting at 1 and going to n. Or similarly, you can mix these integrals, the indices. I'm not going to spend much time on this because, again, nobody really does this. But again, I have to cover it, otherwise I'm not going to get accredited. Okay, so here's a nice little plot just to show you guys what I mean. So the left series literally takes the point on the left side of the interval, and the right one you get on the other side. You could imagine. So here's the true function is 33333. Right, left integral gives 285, right integral gives 385. The problem with this is that if you have a convex or a concave function, you're going to get different results. Right? Your one is going to be better than the other, just depending on which way the curvature is and which side you sample more. So it's not so useful. I'm going to skip over a lot of the derivation of the error. I'm just going to hit the high points here, and if anybody has questions about the actual details, then we can come back to it. All of the error kind of works in the same way, right? This is the template. You take your Fourier expansion. You take your Taylor expansion. You integrate over one of your subdomains, and integration is distributive. So when you integrate over your function, you're just integrating over the different parts of your Taylor series, which is super useful. Yeah. So you can do this, and then you can integrate it term by term, and then you get functions that are either explicitly evaluated in terms of your step size. You get your order out front. And now here's the next trick. So this one, the left and the right are both order h squared on the subinterval. But we have to add up all of the subintervals in the function in order to get the full integral, in which case the overall efficiency becomes order h. Right? So the subinterval is, I think at least in Newton-cotes, it's always going to be one more accurate. So h squared, and the total is going to be h to the 5th, right? Total is going to be h to the 4th, and that's because you're just summing up all of your intervals. So the idea with a midpoint is quite literally now you're taking the middle of that subdomain. When you do it, you get something that looks like this, and you see that the midpoint integral is a whole lot better. So on the one hand, so this is another example. Let's talk about the error first. So the nice thing about the error and taking the midpoint, anybody know why the midpoint's going to be better? You answered a lot of questions for me.
is kind of the average between the left and right hand sides.
Okay. That's one, right? So that's like kind of the immediate answer, right? Because you have something that behaves better convex, concave, you want to be balanced, right? Anybody have any other ideas? You answer a lot of questions too. Anybody from the back? Back 3 rows? Kind of a funny one.
Oh, well, I don't.
Think about the Taylor expansion. Right? When we went through numerical differentiation, what we found is by taking the middle point of these methods, whatever is wrong in front is also wrong behind, and we can cancel those out. With a midpoint method, it's the same thing. Because we're taking a point in the middle, whatever the first derivative, so remember your corrections go by order of the derivatives in your Taylor series, right? The first one is a function value, the first derivative, second derivative, third derivative, right? If we take the middle point here, then whatever our slope is here is the same as the slope down here. And what we can do is we can combine that and cancel it out, in which case we gain an order of accuracy. So here's the explanation. We have to define, if you're going through this, we have to say, I thought I derived it here. Okay, we have to say that yi is the midpoint, and that's just for a matter of convenience to separate it out from your discretization. But the math works out pretty simply. But what you end up getting is that your first derivatives cancel out, and when your first derivatives cancel out, you're left with the next term, which turns out to be an order h cubed, which is pretty nice. In which case, again, integration over the whole domain gets to be h squared. So the math is all there. Go nuts. But that's the heart of it. You take what's before and you cancel it out with what's after it. There is a problem with the midpoint method. That being that whereas before, if we had tabulated data that started here and ended here, we could get the integral between these 2 points. With the midpoint method, we can't really do that because it sticks out on either side, and there's no way to eliminate that. So when you calculate that integral, you're not actually calculating from here to here. You're actually calculating from a little bit past it to a little bit past it over here. Okay? So what that means is that you can use it, but it's not, strictly speaking, the correct integral because you've expanded those limits a little bit, which is where the trapezoid rule comes in. So trapezoid, this time I do know what it is. It's just a four-sided object with a straight line on top. The idea there, this is the first order Newton-cotes, first order polynomial being a line, right? Literally all we're doing here is we're just taking simple, oops. Did I lose you guys? Okay. Thought I heard Teams thing. Yeah. So this is the formula here. What we're doing is we're taking the what is it? We're taking the slope, we're multiplying by the height on both sides, and we get a super concise formula. When we look at the area, it gets a little bit more complicated. What you have to do is you take the Taylor expansion at both sides. So x and x plus 1. Then you take the average. And again, what ends up happening is that the first derivative over here ends up canceling out with the first derivative on the other side. And again, you get that boost in efficiency. Yeah. Blah, 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 blah. You get this, you get order h cubed, and then you have to add up all of your subdomains in your full domain, and you get order h squared in the end. So this is the same sine function for the trapezoid method, and you can see that it just kind of follows this thing, right? But there's something kind of neat. In general, which do you think would be more accurate? The midpoint method that looks like this, or the trapezoid method? Kind of looks like trapezoid should be, eh? The fact that I'm asking it, means that it's the other one. If you actually run that, yes, you can run it. So there are, oops, I put in a little testing thing here. Okay. So we're going to run this test. We're going to calculate it using the NumPy functions, and we're going to see which one is more accurate, okay? So f of x is sine, trapezoid method. Here's our step size. What is the sampling space between A and B? What would you have to put in for the sampling, for your x values for trapezoid? Anybody have any ideas? Trapezoid evaluates. Yeah.
Oh, I was just gonna say like b minus a over your.
Yeah. Right. Trapezoid evaluates at every single point. So for trapezoid, it's super easy. You just say go between A and B in n+1 increments. When you go to the midpoint, though, it's going to be a little bit different, right? So where are we sampling here? Yeah. Right. So if these are the subdomains, all right, this should be even subdomains. Right? There's our limits. So trapezoid is just going to take that side. The midpoint method, we're going to need to know it in the middle, which means you have to get a little bit more complicated with the linear space definition. All you have to do is just add h over 2 on both sides, and then you're good. And let's take a look what it does. Oh yeah, midpoint is nice actually because all you need to do is a sum. That's it. Whereas you need to use the traps function for NumPy to get the trapezoid one. Okay, so sure enough, and not so surprisingly, both are order n squared, or excuse me, order h squared, which means when we double the number of steps or the number of subintervals, who said it? 4, right? N squared, 2 squared, 4. Okay, and what you see is actually midpoint is better by roughly, what is that, a factor of 2. Anybody know why midpoint might actually be better than trapezoid? The errors cancel. Yeah, that's exactly it. In general, this guy, whatever the area of this triangle is here, is roughly the same as the error up here, right? Or the area here. So when you take that middle point there, you're actually effectively canceling out those two errors, which turns out to be better than just ignoring the curvature entirely, right? So this is kind of what I would say is kind of like the point of all these numerical methods is to use the properties of the math, not to necessarily avoid those errors, but to find a way to cancel them out. And canceling them out almost always makes for a better result, which is kind of neat. Okay. What else can we do? Simpsons. Simpsons is still a thing, right? Oh, good. TV show. I remember when the Simpsons TV show. I'm older than the Simpsons.
I'm gonna do it.
Shoot.
Instead of straight lines, you put little quarter circles.
Quarter circles.
Yeah.
Huh? What do you mean?
Put like a little quarter circle. And then it's straight down after it
Like that?
yeah, but like super curved. Like
that?
kind of.
How'd that happen?
I don't know.
All right. Anybody else have an idea? Remember, Newton-cotes does what? Not rectangles. subdivides the problems, and then fits a polynomial, right? We did zero order, we did first order. What comes after 1?
5.
2. Right? So how would you do a second order polynomial here? You need one more data point, right? So what Simpson does is he joins two of these intervals. It's quadratic, right? And then you can just repeat that over here, fit another quadratic, right? Some people might be tempted to try and do something clever where you're going to do like one of these and then one of these and then one of these and then one of these with like that overlap and somehow eliminate the double counting. Nobody does it. I have never tried it. I have never analyzed, but generally speaking, if nobody does something like that, it doesn't, it's not necessary. It's not worth it. So I'm just going to end that one there. The reason why you can do this is because integration is just summation. There's no value to requiring any kind of continuity at all, actually, to these methods, which is kind of cool, even for like completely discontinuous functions. Not really a problem. Yeah, as long as you know where that break is. So we need 3 data points. We can envision it as 2 subdivisions back to back, right? The pair of subintervals is just a conceptualization, right? It just depends. You could quite evenly say that this is actually one subdivision and you actually have a midpoint, right? Like it doesn't matter. It's just a mathematical framework by which you get something that looks like this. So don't get hung up on the idea of gluing these subdivisions together. You could just have one point in the middle of another subdivision. Does that make sense? Yeah. So this is a nice illustration of what it means. You take those points, you fit a parabola. Now you have 2h, right? In our conceptualization, put apples with apples, right? Same thing on the other side. We can fit a quadratic. How would we fit a quadratic? Is that with log? That's a good one. Anybody else have a better one? Is that? Interpolation and a curve fitting. That's one idea. Even better, we know how to fit a simple polynomial, which is, don't even need that one, because that now it gets complicated and it gets hard to find the solution. Lagrange interpolation. That, like, one of the reasons why we looked at that is because it's literally the foundation of almost everything else we do. Like, everything is a polynomial when you get close enough, and the best way to do that is with Lagrange interpolation. This is the formula, in case you don't remember it right off the top of your head. I mean, come on, guys. When you can simplify it by having even even spatial steps, in which case you get this nice factor of h popping out. When you put it together into the integral, you get this beautiful function that actually looks very similar to numeric differentiation. But now we're doing integration, right? And notice that you have a 1/3 h. That 1/3 is why it's called the Simpson's 1/3 rule. When you look at the analysis, what ends up happening is, first of all, you need to do the Taylor expansion now 3 places. In the middle point here, in here, and down here. I'm going to try and get through this so that we don't need to come back to it on Wednesday. And then you kind of smack it together. You arbitrarily put it into this form, calculate everything out, and now what ends up happening is, assuming that the second derivative doesn't change much between here and here, you end up canceling that out. Let's see. Yeah, you end up canceling that out, as well as, you end up canceling that out, and you actually end up with an order 5 algorithm. H5 algorithm, which is, again, very nice. But now, now you have to slap it together for the entire integration domain, and now you're down to an order H4.
If you're looking at maybe like a side function.
Yeah. Now you're into a discontinuous function, in which case all bets are off, to be entirely frank.
Like shape, like a side function, like, you know, it's that's what you're saying, like the second derivative, like.
Yeah. I mean, again, it goes back to the idea that if you go close enough, i.e. if h is small enough to resolve the feature, then it is going to be a parabola. And it is roughly going to be a constant on either side of that. In which case you can use the information from one side and the information from the other side, again, to cancel out those errors and therefore get a better estimate. Problem with this. Anybody see the problem with this? This is pretty clean, dude. The fact, right, that this integral. Hold on 1 second. I have to harp on this for a second. So the fact that this integral is just like what? The sum of these different points times h over 3 is actually pretty impressive. I gotta say, like that's normally we think about these things as being like complicated integrals and stuff. Like the finite difference, the numerical one actually works out pretty cleanly. Who sees the problem?
But I don't.
Yeah. Anybody see it? We're running out of time here. How many intervals do I need? Right? Or 2n. Yeah, I need an even number of intervals, right? Which is a problem because if I have an odd number of intervals, then I would have to combine this with something to give me that last interval. And when I add everything up for the whole thing, then whatever my accuracy is going to depend on that bad one over there, right? And it's going to spoil my nice order 4, excuse me, for the total, right? No. So this is a super quick example. Feel free to run it on your own time. Give me 1 second here. What you see is that the Simpsons error decreases, like drops like a rock, which is really nice. Let me just get through this and then I'll come back to your question. Okay. Simpson's 3/8 rule is in order 3. In this case, what we're doing is fitting a, what's after 2? Right. It's a cubic. So we're taking 3 intervals. Third year engineering physics. 1, 2, 0, 1, 2, 3. Good. Right. When you crunch the math, you get something that looks like this. Notice it has a 1, 2, 3, 4 data points, but you still only get order 5. So comparable for the subinterval, which means when you integrate and add everything up, you still get the order 4, right? So that's a little bit funny. And actually, basically nothing beyond this is really worth it. Simpson's 3/8 is where almost everything stops. The nice thing about this is that now you have 3 intervals. So if you have even is better because you only need the different functions, but then you can combine the even and the odd, and therefore you don't have a problem. So if you look up the numpy function, I think it might be a sci-fi function for Simpsons. It doesn't care about the number of intervals because it automatically does that for you. Question. You got it? Okay. I'm just gonna wrap up this thought and then I'll stop for the day. Yeah, so this property that higher and higher derivatives, higher and higher polynomial orders don't actually end up increasing the error is kind of what stops this this series from continuing on larger. So most people at this point will kind of arrive at that balance between the 2/3 and the 1/3 and the 3/8, and then that's how they get the thing. I'll come back on Wednesday, just talk about the uneven data and the multiple dimensions. Spoiler alert, multiple dimensions is super easy. Uneven data is a bit harder. Any questions? Excellent. Class dismissed. And here. So uneven data with
I have a question.
Oh, shoot.
Just curious, how many marks would you have lost if like you did polyfit on the last question?
Technically, you don't need to polyfit on the last question. That was actually a little bit of a red herring. What you do need to do is some kind of minimizer to so you could do LSQ, for example. Any of the least square, the curve fit, or any of the minimizer algorithms will also work.
All right.
Okay. Cool. So uneven data. When you're doing switching gears, numerical integration. Having the same step size both within the subinterval and between intervals is your best guess, is your best way to do it because of that error canceling phenomenon where you can cancel out all those higher order terms. If you can't do that, then the problem is that it's the overall error on your integral is kind of determined by your smallest, by the largest of the subintervals, which is a bit problematic, to be honest. Yeah, you could always do something like trapezoid method on it, like the first order derivative, like it will always work. Ideally, and usually if you get something that has uneven spacing, what you're doing is some kind of experimental technique that does like sampling at one frequency up until a threshold, and then you sample at a much higher frequency. And you want to integrate over the whole thing. In which case, what you get is, right? So you're going to get something like this for time. You're going to get la, 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 really slow, super fine, right? La, 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 super slow. When you do that, what you want to do, and a lot of the normal techniques, a lot of the package tools will be doing all this automatically, right? So it'll identify, hey, this group is continuous. Hey, this group is continuous. Hey, this group is continuous. And it'll treat them accordingly. So you do Simpsons 1/3, Simpsons 1/3 / 3/8 for this one too, and then you slap them all together. So you're still getting, you know, the chain is only as strong as the weakest link. You're still getting the uncertainty from the largest subdomain, but at least it's order H, I think it's H cubed at that one for Simpsons rules, right? And then you combine the 1/3 and the 3/8 to get your full thing. You're even and your odd functions. Bum, ba, bum, bum, ba, bum. Yeah, in cases where you do have uneven data, it's not uncommon that you would have the ability to sample with your own terms. In other words, you would have not tabulated data, but you would actually have a function that you can question. And that's what I'm hoping we'll get to today to talk about that one. Because that's really cool. Multiple integrals. Good news with multiple integrals, they are naturally decomposable. So you can do an integral in one dimension and then do an integral in the other dimension. So there was a neat plot, I guess I never got around to actually putting it in. But the idea is if you have big 2D square, right? You integrate like that, you get something. You integrate like that, you get something. Right? This is all evenly spaced. You integrate like that, and then you integrate down that way, and everything works out super clean, which is nice. Finally, there's some good rules, some good news about numerical methods. Here's a little table that I cooked up to help. Okay, that's order H4, not H3 for Simpsons. Just to help you guys if you need like a convenient place where everything's all together. I don't know why the markdown like kind of wraps these lines here. No matter what I do, I can't get it to straighten it out. Okay. Any questions for numerical integration with basically tabulated data? Or we can get into the cool stuff. All right. In the case where we have a function that we can actually evaluate. So maybe this is something like we have some numerical function and it's a black box, we don't know. Maybe we're doing finite difference methods. Maybe we're doing finite element or something like that, or robotic applications or anything like that. Anything where we will be able to control sample point is, we can throw either the Romberg technique or the 2-point Gauss-Legendre technique, or not 2-point, the Gauss point methods, okay? So the idea here is, it's kind of a neat observation, right? Any integral, so sorry, let me back up. The idea is that we're going to apply successive approximations to the same interval in order to get to an arbitrarily high order approximation of the integral. So this is one of those, like we can tune the tolerance and we can hit it. The observation is that the true integral is equal to the approximate integral plus the error. Wow, genius, right? With a lot of these methods, for example, the trapezoid rule, we know what the approximate error looks like, how it goes like. In particular, it goes with h squared for trapezoid. And in fact, when you go down into the math, unsurprisingly, because it's Taylor expansions, it actually turns out to be f double primed, right? Second derivative of f with h squared in there. If we assume that f double prime doesn't change, and we just resample the same domain, right? Before we did like this, now we do like this. Let me try and clean that up. So this is h1, this is h2. We can compare those answers. And we know that they're both approximates of the same exact integral. Okay? So what we can say, because we know the form of the error through Taylor expansion, we can say that there's a ratio between the errors from step size 1, h1, and step size h2. Specifically, that it goes like h1 squared over h2 squared. Plug it into the equation that both the exact integral is the same, no matter which step size you use, right? So this is the approximate from h1, the error, approximate from h2, the error from h2. Now we can remove one of these terms. Isolate for the error from h2, pop it into this equation, and what we've effectively done is eliminated that second order derivative, which is kind of neat, right? We didn't even approximate what it is, but just by comparing two successive step sizes, we can actually give what turns out to be a very good estimate for it, to the point where just by doing this, we achieve order H4. So we've doubled the order of the approximation just by resampling it. Generally, you want to subdivide by 2, right? So if H1 is this, you want H2 to be that way, because this way you can reuse your data, right? You've got that data, you've got that one. That doesn't change depending on your sampling frequency. So your next one, H3, would be something like that in the middle. Da, 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 da. Yeah. Yeah. Go for it. I don't know. That's an excellent question. I honestly don't know.
Sorry, could you repeat the question?
Yeah, the question was that if we had tabulated data that was on the order of, this higher frequency one, would it make sense to apply the same methodology, just subdividing those parts?
Oh,
And actually, that's a very good idea. I don't know if that's a thing.
thank you for repeating it.
No, absolutely. Thanks for pointing out that you can't hear it. Okay. So what this boils down to, once you group all your terms and everything, is that your exact integral is approximately, and then there's this weighting between your highest precision integral, approximate, and you're subtracting off a little bit from your lower one. That pattern is actually repeated, so you can do this recursively, and you can get from order H2, 4, 6, 8, however many you want, just by subtracting off more and more of these iterations. And what you get is it weights it more and more towards the higher frequency sampling method, but you still achieve that next jump just by subtracting off the previous one, which is kind of cool. This is the general formula. This is what you're going to see inside the, I think it's scipy.romb. We'll give you that. And this is where that formula comes from. Note also that it's a redundant problem, right? Generally, redundant problems are more or less elegant usually more efficient, and it parallelizes, right? Because you could do integration on different domains, you could slap them together, you could do all kinds of different things. Okay, let's approximate the integral from 0 to pi sine x, like we did last time, with Romberg compared to the Simpson's 1/3 rule. This is a little code that does it. And what you see is we start off with yeah. So with 4 intervals, we shrink, we get very small, even smaller, and then eventually we get to 0 with 128 intervals. You guys remember what 0 is? Well, we just answered this question, right? That was one of the quiz questions. 0 is just that we've exceeded finite precision, in which case there's no point to repeating this past that point. Any questions? Okay. Let's talk about Gaussian quadrature. Spoiler alert, Gaussian quadrature is the fundamental tool in finite element programming. So we're going to be coming back to this one. Until this point, we've been using techniques where we've given our sample points and we've been told to use them, right? We say we're sampling here, 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 here with a fixed step size. Let's relax that. We can gain, keep that in mind, and at the same time, remember that we can gain an accuracy by canceling out the positives with the negatives, okay? This is the whole point behind Gaussian quadrature. What we're going to try and do is we're going to try and find magic points, they're called Gauss points, in the interval where we evaluate the function and it turns out to be the integral, which is pretty cool. The textbooks like to start off with rederiving the idea of the trapezoid rule to give a bit of a framework. In a nutshell, what you want to do is say that, okay, trapezoid rule has to be exact when you have a straight line. Right? Trapezoid rule is a straight line. Therefore, if you are in one of two cases, either you have a constant function or you have a function which is just a straight line, you have to get the exact integral. Okay? So we write those two down. We say the integral of, oops, where is that? I think I missed a line here. Here we go. Sorry, let me just correct that one there. That's better. Okay. So this method is derived from something called the method of undetermined coefficients. Basically, what we're doing is we're going to say that it's the integral is equal to constants C0 and C1 times the function evaluated at 2 points. Okay, this is the trapezoid rule, right? We already looked at this. So for the case where we have a constant, f is 1, so what you do is you write out your functions where this integral has to be exact. And then we're going to work out what these scalars are going to be, what these constants are going to be. So for f is equal to 1, you get I is equal to, well, what's f at anything when f is equal to 1? It's always going to be 1, right? So you get C0 times 1 plus C1 times 1 equals, and then you do your formal integral, which comes out to your step size, b minus a. Okay? Then you repeat the procedure, now with a function which is a straight line. Again, it has to be equal. And because we're doing this in kind of an abstract thing, what we're doing is we're centering a and b over 0. Right? So we're doing a simple one. We've got that, that's a, that's b. Okay? When we do a line, f is equal to x, right? What's the integral? From a to b of f is equal to x. Going to be 0, right? Because whatever the triangle is over here is equal to that. You cancel out. But what it gives you is another equation. So now you've got two equations. You've got two unknowns. Your unknowns in this case is C0 and C1. You solve for those and you get trapezoid rule, Great. Okay, let's take this a step further. Let's say that we still have the same form, right? Constant 0, 1, function at x0, function at x1. Now let's let x0 and x1 float in that domain. And let's require, since we have 4 unknowns, right? C0, C1, x0, x1. What do we need to fix 4 equations, 4 unknowns, 4 equations, right? Let's repeat that exercise for a cubic, right? And a cubic, remember, can be maximum order x cubed, but it also includes everything below. So let's rewrite this, right? For the constant 1, f is equal to 1, we get an answer. F is equal to x, we get another one. X squared, we get 2/3. X cubed, we get 0 again because it's symmetric odd function. And we solve. Right? Standard linear solver. Actually, no, this isn't linear, right? Because this is a nonlinear solver. We solve it. What we get are these. C0, C1 is equal to 1. X0 is negative 1 over root 3. And 1 over root 3 is the other one. What this means is if we have so here's our A, here's our B. You might have noticed that they've changed the integration limits from -1 to 1. We're going to see how they do that afterwards. Just bear with me at this point. What we're going to do is we're going to take any interval and just rescale it and then apply this method. That's why all these integrals are from -1 to 1. Okay? So given that this is -1 to 1, all you have to do is evaluate at -1 over root 3 and 1 over root 3. And you add up these two function values and any kind of weirdo cubic, I guess that wouldn't be a cubic, solves exactly 100%, which is kind of neat, right? Da da da. So let's test this. I don't have time to go through the SymPy. I was hoping to use this as an opportunity, but feel free to take a look at it. Right. So all we're doing here is we're just evaluating it at -1 over root 3, 1 over root 3. We're just adding it up. Very quickly, SymPy is symbolic logic. So what you have to do is you have to declare your variable, that it is a variable in Python. You can use these functions called lambdafy, which takes a SymPy expression and makes it into an executable code. Don't need to worry about that, but it'll also do integrate for you. And that's the magic. Okay. So what I did here was say, okay, this is the function. This is the correct integral. And here's the error. Here are some nasty functions. We've got a quadratic. Can you guys see the screen here? There we go. Right. We've got x. Okay. X squared should definitely work. This is just me making stuff up and being kind of nasty. Pi times x plus 17. 10 to the 9, right? We're making order of magnitude 10 to the 9. EXP of 8.314. We've got a pi in here, 42. And in each case, we've got exactly 0 error, which is, honestly, like the more you learn about math, the more you realize why like Gauss, Euler, like Legendre, Newton, I guess, Newton, right? But like madness. Okay. To apply Gaussian quadrature to an arbitrary domain, i.e. from A to B, all we have to do is scale it. Okay. So what we're going to do is we're going to define a coordinate transform. We're going to run through a bit of algebra and we're going to get an equation that looks something like this. And what you do then is that you put that into the Gaussian quadrature formula, right? So you take your, and this is important because it comes back in finite element method too. And it gets more complicated there because now you've got 20. Okay. So what you want to do is you want to take an arbitrary domain that's over here. And you're just doing a coordinate transform. You're basically defining a new coordinate xd that goes from -1 to 1 as this is going from A to B. The math is there. Feel free to turn through it. I don't really have time to go into it, but it does work. Why do I say that? Because it's super easy to implement. And then you can say that this is going between anywhere. So this is 0 and 1, but you could do it any other interview. Feel free to play around with it. We could do endpoint Gauss-Legendre formula. So we did 2. And 2 can integrate exactly up to a cubic. Mind blowing, right? We could do more. These are called the order of integrations. When you do Gauss points, the integration order is the number of points that you're using. The points themselves are called Gauss points. And then you've got your coefficients here and the associated error here. I doubled up on my plus minus here. So just be aware that this is actually 4 terms. It's just the permutations of plus and minus. Otherwise it gets a bit too messy. When you look at the error, you see that it's proportional to the 2n plus 2th derivative, right? So in this case, it's going to be for the 2 point, that's going to be 4 plus, what would be 4 plus 2. So this is actually the 6th order, which is mind blowing how good this thing is. When we want to move into multiple dimensions, hope I'm going to get this in 3 minutes. Yeah, so multiple dimensions kind of works because of the separability of integration. You could do the same idea as up here, but there are better ones that are more optimized. So the first one is for quadrilateral elements. Quadrilateral being, well, that. The exact same idea. First of all, you want to take your whatever your quad element is and map it onto this square. I don't think this is called the unit square, right? I think unit square is explicitly 0, 0, 0 to 1, 1. You want to map it onto the -1, 1 square. And then you can follow a similar procedure to find where your Gauss points are. All you need to calculate is what your function values are at those Gauss points. And what we're going to see in finite element, we don't actually need to solve anything else or calculate anything else. All we're actually going to be solving for is the value of the function at those Gauss points, which is going to be neat when we get around to it, but this is why we're doing that. So this is all about the transformation. We also have to be aware, so there is a mapping distortion that goes on between having this quadrilateral, because we're actually changing the shape. There is a bit of an area distortion. We have to throw that in. That turns out not to be so complicated. Honestly, like at this point, we're into package territory when you look into Gaussian quadrature, but it is kind of important to know what's happening here. Okay. Quads are nice, and they're actually good in finite element when you can get them. The problem is that you can't always get them. If you're getting something that is a wedge shape or something like that, you're going to get a degenerate quad at some point where one of the sides goes to 0. What is a square where one of the sides goes to 0? It's a triangle, right? So why don't we just start with triangles, to be honest, considering you can always make a quad out of 2 triangles. Okay? There are actually reasons. Maybe Andrew will tell you about the reasons. Right. So let me wrap this up. The mapping gets more complicated, to be entirely frank. Getting from these triangular 1, 2, 3 to something that Gaussian quadrature expects is tricky. The math is here. I don't have time, and I wasn't planning on going into it anyway. But again, the whole idea is that you can find your Gauss points, right? For linear elements, so this is order 1, you get just in the middle, the, what do you call this, barycentric middle, right? For quadratic elements, you have to get them on the sides of the edges. For cubic elements, you get them that look like this. These are the weights associated with them. I would never expect you guys to memorize all this stuff. Yeah. And that's it. Oh, sorry. Tomorrow. I'll send it out tomorrow. Yeah, actually we have negative time. Negative overtime, good. I am going to move to the 1 assignment for every 2 weeks method, because, and the idea being that we'll have Monday's class to work on the assignment. So Monday's lab, We can work on the assignment. We can potentially even complete the assignment, but then the following Monday, we're gonna follow Minix style, where like you hand it in, I don't know, maybe on Thursday or something like that. I'll update you guys. And then we'll have like a few days for the TAs to generate some questions, and that way it's more targeted to your particular assignment. So we can ask questions like, what does this do? But that way also like we'll have time to prepare the oral questions beforehand. So that was kind of a problem in the past, that like, we ask you the questions and then it takes a while to put the marks out. And then you get a mark that isn't actually tied into anything that you can actually improve. So this way it's going to be more formalized. It'll probably mean that we're all going to have to do one TA per person for that discussion part. But I think that's a bit more sustainable. I am going to try and keep it so that at least we can get the bulk of the assignment done during the Monday last session, or at least to the point where, you know, it's a matter of tidying stuff up afterwards. So expect that tomorrow. I've got a big deadline at 4 o'clock tomorrow, so it might not come out till tomorrow at like 6 or something. Thanks for the question. Okay. Anybody else?
Can I ask one?
Yeah.
I don't know if anyone's talking in the room, but
No, go for it.
if we're gonna have the assignments every 2 weeks, could you add more of those like brainy critical thinking, like go an extra step type of things? Like for like that, I don't know. I don't know if I was just stupid for not thinking of that second boundary condition, but it's like exactly like you said. It's like it's something that's like, you know, logical that you actually have to think about. I know the reason why I didn't do it was because I hadn't done it in an example or hadn't seen it in an example before.
Yeah.
But you know, would it be
I'll
possible?
try.
Yeah, okay.
I'll try. I mean, the assignments, like now that we're into the material that's a bit more multi-leveled, like
Yeah.
with the finite difference, like that's actually something that you guys are going to be using in the future. And that's
Yeah.
actually something where I can give you a question like, work out the heat transport through this odd geometry,
Mhm.
right? What if it's temperature dependent, right? Like now we can actually start to play around with that. The same with the integration.
All right.
Yeah. So, but I'll see if I can cook up something interesting.
All right. Thank you.
Thank you. Yeah. Oh God.
What tables like this were useful to look up? If we needed it for a question, would you give it to us, or would
Yes.
it be like on our?
Yes. Yeah. I mean, there's no reason to knowing this stuff. It's not even, apparently these are actually roots of Legendre polynomials. By the way, that's actually how they work out the Gaussian. Like there's no reason to memorize that sort of stuff, right? Like that, the whole point is Gauss quadrature, super cool. 2 points gives you cubic accuracy, which is awesome. Anything else? Happy Halloween.